Okay, now let's start to look at ground clutter in depth. We're going to have an introduction, and then we're going to study the mean backscatter of ground clutter, its frequency dependence, terrain type and polarization. Then we'll look at the temporal statistics and the Doppler spectra. And that seems like a little bit, but it's really a cursive dimensionality, given that there are so many different frequencies, so many different terrain types. Luckily, there's just a couple of polarizations. And we've also got environmental backgrounds, that the wind can be blowing or not blowing, that sort of thing, which will affect the Doppler spectra of the background in forested areas. But let's go in and take a look, starting with an introduction. The mean value of the backscatter from ground clutter is very large relative to the aircraft. I've shown you that earlier, and it varies statistically with frequency, spatial resolution, geometry, and terrain type. And the Doppler characteristics, there's an innate Doppler spread that's a few knots, and we're going to see it varies somewhat. And a big effect on that innate Doppler spread can be the mechanical scanning of the antenna, which amplitude modulates the signal, and it can add significantly to the spread of the clutter. And also, the Doppler characteristics of the ground clutter return depend on the relative motion of the platform and the ground clutter. Now, if the radar platform is on the ground, there's no additional relative motion. It's just the Doppler motion of the ground clutter. But if the radar is on a ship or on an aircraft, then that relative motion will take into account and moves significantly where the Doppler spectrum is. And that will, in the case of aircraft, it will make the Doppler spectrum vary with aspect angle relative to the ground, the speed of the aircraft, and what have you. And we're going to go look at those things in detail. Okay, now the first thing I want you to, you'll see or have seen maybe before, a plane position indicator. And this was the first display device. Well, it's really the second. I won't get into an A-scopes, which we used earlier, but for still on the FAA radars, they have a mode where they can look at the analog return. And you notice this line going around. It's a map-like display. It measures the radial distance from the center. These rings correspond to increments of range from the radar, say 10 miles, 20 miles, or 25, 50, and the angle of the radius vector. Now, this front edge shows you where the radar is pointing. And notice that it's a fluorescent display, and so it dies with time. It has a fall off in intensity with time. And it shows you all the threshold crossings, and when we get down here, we see a target which slowly dies. Okay? So you can see the range azimuth detections raw with a PPI display. Now, when we take and we go to a mountainous region in Lakehead, Ontario, Canada, and the PPI is set for 30 miles, and you take a long exposure photograph of that display, where we see black, there were no threshold crossings above the minimum detectable signal of the radar. So the threshold of this, of the white, is just the minimum detectable signal. And what we see obviously here is a huge amount of clutter. And this is with no attenuation put in the input. So it can be clearly said then that aircraft could not be seen in this clutter region. Going to have to do something about it. Now, for one thing, we know the clutter doesn't move very much. We'll get into the details of that later. But to first order, it's probably doesn't move. It's mountainous. And so, this obviously isn't showing that region, or it'd be all white. That light target would be, if it were in there, it'd be white too. Okay. Now here is that same photograph with 0 dB of attenuation, but if we put in 6 orders of magnitude of attenuation into the input signal, we see we've gotten rid of a good deal of the clutter, but we still haven't gotten rid of all of it. And that truly is an amazing thing. The clutter is huge in this case. And I've deliberately picked a very heavy clutter situation to show you in this example, so that you can see it is heavy clutter. Now, if we look at the same data with different levels of attenuation going from 0, 10, 20, 30, 40, 50, 60, and then even up to 70 dB of attenuation, you can see that there are certain ridge lines that are a particularly high clutter that are clearly 1,000,000 times more backscatter than the minimum detectable signal. And it takes another 10 dB to get rid of them. And they're probably 25 miles away from the radar. And if you designed a clutter suppression system that could only handle 30 dB of clutter, these are all going to come through, and they're always just going to appear like tracks. You'll get every single scan. And someone could fly through that area, and you'd never know they were there. So the question is going to be, how do we solve? And this is just the first clutter problem. First, let's look at the geometry next of radar clutter so we can get a feel for the nomenclature we're going to use. Let's assume the radar is at height h. Here's its antenna. It's got a depression angle phi, and the range cell size is the speed of light times the time divided by 2. And because of this, it's looking down at an angle. It's c/2. It's 1/2 ct times the secant of the depression angle. And that's the elevation angle. When we look from above, the clutter is out at a range r, and with a beam width of the radar theta sub b, this is the area that the clutter that you see. And the backscatter you get here with a constant time is certainly less than the backscatter you'd get, is more than the backscatter you'd get here. So you want to take out that range dependence, and the way we do it is we take this quantity, the area, and we take the cross-section that we see of clutter divided by the area, and we have a quantity called sigma 0, which is the radar cross-section per unit area. Okay, the typical value of sigma 0, the cross-section per unit area, for this kind of terrain, you know, forested terrain, an average number might be minus 20 dB, and in the units are meters squared per unit meter squared. And the clutter cross-section is equal to sigma 0 up there times the area. Then the cross-section of the clutter would just be this quantity here. So we can fill those in for an ASR 8 or 9, which have the same ranges and beam widths. And first of all, the pulse width is the speed of light times the pulse width divided by 2 is about 100 meters. We'll look at a range of, say, 60 kilometers from the radar. That would be 60,000. And then we put in the beam width, which is about 1.5 degrees, which comes to 0.026 radians. And that gives us order of magnitude, I'm doing this calculation, 1,500 meters squared of cross-section. That's the cross-section of the clutter. A typical Piper Cherokee in the nose-on general area is about 1 meter squared. So the input into our signal processor would be 1 over 1,500. And we typically like about a 13 dB or a factor of 20 output of the target being bigger than the clutter. So we must suppress the clutter by a factor of 30,000 or 45 dB, and this is just for an airport surveillance radar at a range of 60 kilometers looking at a 1 square meter target. You still need to suppress the clutter by a factor of 45 dB, which is no small feat. If the clutter is larger and the cross-section is a lot smaller, then it just gets bigger and bigger. This number gets huger and huger. Now, to understand and do a first-rate set of measurements on what the clutter is and in a large areas in the northern temperate zones, Lincoln Laboratory, jointly with Canada and the United States government, set to do in the mid to the early 1980s a measurements program to measure clutter. And they measure it in all these places where there are dots. And there were measurements that were made with the system outside of this specific ground clutter. Some looked at sea and other things, but I'm only going to talk about the ground clutter here. And this is the phase 1 radar that was used. It could collect data at VHF, UHF, L-band, S-band, and X-band. That's from 3 centimeters up to the order of a couple of meters, 1.5 meters. And it was measured between 1982 and 1984. And that data is archived at MIT Lincoln Laboratory. And the data is shared with Canada and the United Kingdom at 42 sites. And these are the analog kinds of regions that these measurements would be good for. It is the most comprehensive ground clutter measurements program that I know of. And it took place over these 3 years, but key to this program was Barry Billingsley from Lincoln Laboratory, who spent with colleagues from, I know Alfonso Farina in Italy and many others throughout the world, analyzing this data to do an enormous amount of clutter work over a period of 15 years. And Barry was awarded a high award from the IEEE's Aerospace and electronic systems for the this career work, and he wrote a book about it, which can be which is referenced in the references. Now here's the phase 1 radar. We see the different frequencies and the gains of the antennas and the different beam widths, azimuth and elevation, and the peak powers, polarizations, the PRFs. And notice there are 3 different pulse widths: 1/10 of a microsecond, 1/4 of a microsecond, and a microsecond, with uncoded CW pulses throughout, and with lots of dynamic range, 13 bits in the A to D converters, and with different sampling rates of from 10 to 1 megahertz. And here's a picture of the antenna with its different antennas back to back, where it could collect data, and this is a forested area. Now, looking into what this radar would see, I'm going to go over a little bit the clutter physics. Now, the clutter coefficient, sigma 0, is going to depend upon a bunch of different factors. It's going to depend on the depression angle, the terrain that's visible. This house is visible. The range, the height, areas which are micro-shadowed by changes in the elevation. And they all contribute to the clutter coefficient sigma 0. And now, also, if you remember back into the propagation lecture, folded into that measurement of the clutter coefficient is the propagation factor, which you can't take out. And for to show you how this varies for, in this case, forest and X-band and UHF, you can see that there's a 13 dB difference in the sigma 0 F, the propagation factor to the 4th power, a 13 dB difference, and the blue line is the mean. The 99 percentile mark is here and here. So if for forests, if you want to see 99% of the targets, you know, you've got a lot of work to do. And for farmland, here and here, you can see that it's way down for VHF, minus 55 dB. And it's minus 23 dB for X-band farmland. And the 99 percentile is just 22 dB and 54 dB. And these histograms of the different places they looked, and they identified the patches that were of the different nomenclature, different kinds. So you can see there's a lot of variation in these. And this, of course, is just a tiny microscopic portion of the data. Now, the next thing one wants to do is one wants to statistically analyze the spread in that data. And Billingsley used the Weibull distribution, which is a 2-parameter distribution, which is often used for describing clutter which has long tails. And it's the Weibull distribution here, and it's got a width, A sub W is a function of A, and it's got a mean, sigma 0 W of F. And here is the Weibull probability density function. It's a rather complicated beast. Log normal distribution and the Weibull distribution are used to model ground clutter because they are 2-parameter. Please excuse the the wrong 2 and 2, it's TWO, parameter distributions, which allow for skewness, long tails in the distribution, which you noticed before. And for A sub W equals 1, the Weibull distribution degenerates into an exponential distribution in power, a Rayleigh distribution in voltage. And in Barry's book, he has a whole appendix about the Weibull distribution, for if you're interested in the details of it. But notice it has 2 parameters. It has the B and the median value. Okay, now if we have to go and we look at the propagation factor, which contributes to sigma 0 F, the clutter strength that you actually see at the radar, there'll be lobing, because part of the beam will bounce off the ground and reinforce and destructively and constructively. And that will contribute to what you'll see. And so that there are a number of different parameters that contribute. We haven't told you yet about, well, we haven't shown you visually, but certainly the frequency, we showed you through the data that one of the radar parameters is certainly a factor, the frequency, and the spatial resolution. The geometry would be the depression angle, range, and height, and the kind of land, the land cover and the land